Section 13.6, the binomial theorem. So in this section, you're going to see that we have combinations have applications beyond just probability, like we've been doing. So over on the left, you see something that's called Pascal's triangle. So the pattern is that the first row starts with 1, and then the second row also has a set of 1s. So the 1s are going to actually stay on the outside this whole time. And then you get the 2 in the middle because you form a V from two numbers, add them together and get 2. So 1 and 2 give you 3, 2 and 1 give you 3. So if we continued, we know that 1's on the outside, 1 and 3 gives you 4, 3 and 3, 6, 3 and 1, 4, and then 1 ends. If we kept going, we'd have 1, 5, 10, 10, 5, and then 1. And this can keep going past 6 rows and really to infinitely many rows. So over on the left, we know that C stands for a combination, and this is the way that we have seen it expressed in the past. And now with what we're going to do, we're going to change up the format a little bit and write it vertically like this. So we know that C n choosing R is the same thing as n over R, which is still said, n choosing R, which all boils down to this formula that we've done in the past, and then same calculator instructions because it's still a combination. So in our calculators, if we did 4 choosing 0, then if I did the formula, I would get 4 factorial over 4 factorial times 0 factorial, which gives me 1. The next one would be 4 factorial over 3 factorial times 1 factorial, which would give me 4. And I'm going to keep this going, and we're going to make a connection. So with the completed row, I'm going to ask, okay, well, where else have you seen 1, 4, 6, 4, 1? And the answer is in Pascal's triangle for row 5. So you can either use Pascal's triangle to formulate the numbers, or you can use combinations, and we're going to do both. So why do we care about this? Well, we're going to talk now about binomial expansion. So looking at the problems to the left, we know that anything to the 0 is 1. We know that anything to the 1 is itself. And then we've actually done this before. Remember not to forget your middle term, where you write it twice and then expand it just by multiplying A to both terms and then the B to both terms. Then I could ask you to do it 3 times. That would take a lot of effort. But if I were to ask you to do it 4 or 5 times, that would just be rude. It's too much and too much of a process. But then how do we expand it? So we're going to use Pascal's triangle or combinations, whichever you prefer, to formulate this binomial expansion. So if you notice, for being squared, we have a coefficient of 1, 2, 1. And that's Pascal's triangle, row 3, or it's 2 choosing 0, which is 1, 2 choosing 1, which is 2, or 2 choosing 2, which is 1. Now, how do I know to start with 2 on top? You go back to the exponent that you're asking to expand it by. So again, if you go to row 4 on Pascal's triangle, you're going to see 1, 3, 3, 1, or you can do 3 choosing 0, 3 choosing 1, 3 choosing 2, and 3 choosing 3 in your calculator, and you will also get 1, 3, 3, 1. So combinations and or Pascal's triangle will give us the coefficients of our binomial expansion. So moving down a little bit, 4 choosing 0 is going to give us 1, 4 choosing 1, 4, 4 choosing 2, 6, 4 choosing 3 gives us 4, and 4 choosing 4 gives us 1. Now those are just the coefficients in front. So how do we know what to do with our variables? All right, so going over to the right-hand side. a couple things to realize, recognize, and then to remember. The powers of A are going to decrease by 1, while the powers of B are going to increase by 1. And this is, again, as we're reading left to right. Then something else to remember is the sum of the powers of each term. Terms are separated by addition or subtraction symbols. So if you were to add up the sum, or the exponents, the sum would be the same as the exponent of the binomial. Meaning, if you looked in this example right here where we cubed it, you have only one exponent, which is 3. You have 2 and 1, which gives us 3. A has an exponent of 1, and then B is 2, which gives us 3, and then 3 is 3. So each term, those exponents add to give you the binomial, the initial binomial's exponent. And then the number of terms you're going to have when you expand is the initial exponent plus 1. So for that cubic function, we have 3, so we should have 1, 2, 3, and we have 4. 3 plus 1 is 4 terms after we expand it. So knowing this, let's go back to when we took it to the 4th power. Again, A is going to decrease, so we start with A to the 4th, A to the 3rd, A to the 2nd, A to the 1, and I'm going to write A to the 0, even though we know that it's 1, but just for the sake of going all the way down to 0. And then B decreases, so B now starts at 0, increases. B starts at 0, then we have B to the 1st, B to the 2nd, B to the 3rd, and B to the 4th, and that's our binomial expanded when it is taken to the 4th power. So if we were to take this binomial A plus B to the 5th power, we're going to start with 5 choosing 0, which gives us 1. Then we're going to continue with 5 choosing 1, which gives us 5. 5 choosing 2 gives us 10. 5 choosing 3, also 10. And then 5 choosing 4, 5. And 5 choosing 5 gives us 1. Or again, you could know how to recreate Pascal's triangle and know that it's row 6. So just like we said that the number of terms is the exponent plus 1, so is the row in Pascal's triangle. So if we're taking it to the 5th power, we're going to look at row 6. So then A's go down while B goes up. A to the 5th, A to the 4th, A to the 3rd, A to the 2nd, A to the 1st, and then I'm not going to write it this time, A to the 0. Then our first term is B to the 0, I'm not going to write it. Then we have B to the 1, B to the 2, B to the 3rd, B to the 4th, and then B to the 5th power, and that is our binomial expanded to the 5th power. So what you have up top there is just the general formula of what we just did. It looks a little confusing, but if you remember the things to remember in the box and then just practice, then you won't necessarily have to analyze this formula, but it's always good to see what that looks like as a general definition. So now we're going to try to expand A plus B to the 6th. And I want you actually to try this one on your own since it's similar to the previous ones that we've completed and see if you get what I get. So I completed the first row with my combinations, and then I did those combinations in my calculator, or you can look at the 7th row of Pascal's triangle and notice that the coefficients go 1, 6, 15, 20, 15, 6, and 1, and then you can simplify. Okay, so these examples that we just did and this one we just did are pretty simple. You can do them pretty quickly, but where it gets a little bit more involved is where we have coefficients, like in this example. So what we're going to do is our first full term is 3x and our second is 2y, and that's important to note. So I'm going to start by writing my combination, 4 choosing 0. And then I have a. Instead of it just being a, now a is 3x. So I have 3x to the 4th power. I have b, which is 2y to the 0, so I don't need to write it, plus 4 choosing 1. A is still 3x, but now we're taking it to the 3rd power, while we have b, 2y to the 1st, plus 4 choosing 2, 3x to the 2nd, 2y to the 2nd, plus 4 choosing 3, 3x to the 1st, 2y to the 3rd, and then lastly 4 choosing 4, 3x to the 0, which is 1, and then we have 2y to the 4th. So now my next row is going to be each one simplified. So 4 choosing 0 is 1, so I have 1 times 3 to the 4th, which is 81, and then x to the 4th, plus 4 choosing 1 is 4, times 3 to the 3rd is 27, x to the 3rd is x cubed, and then we're going to multiply it by 2y. 4 choosing 2 is 6, 3x squared is 9x squared, 2y squared is 4y squared, plus 4, 3x times 2y cubed, which is 8y cubed, and then we have plus 1 times 2y to the 4th, which is 16y to the 4th. So now we have multiple numbers in each term. So yes, you see the 1, 4, 6, 4, 1, which is row 5 of Pascal's triangle. But our final answer, those numbers are totally going to increase because we are going to multiply them by the number that we have in that term from squaring or cubing 3x or 2y. Now that we have coefficients in the initial binomial, this is what happens. So let's simplify. The first term stays 81x to the 4th plus, all right, we're going to do 4 times 27 times 2, which is 216, and then I'm just going to put my variables together, x to the 3rd, y, plus 6 times 9 times 4, which is also coincidentally 216, x squared, y squared, plus 4 times 3 times 8 is 96, x, y to the 3rd, and then plus 16y to the 4th. So what you see in red here is our final answer. I highly recommend that, as much as it is a lot to write, you do each of these steps so that when your paper is graded, the process of where you got, or if you accidentally messed up in multiplying, it can be found and partial credit can be given. So now we're going to do another example with coefficients. However, we have a subtraction sign, so let's see what that does. All right, so we start with 5 choosing 0. A is 2a, so we have 2a to the 5th power, and then that b values to the 0. Then we have 5 choosing 1, 2a to the 4th power, plus 5 choosing 2, 4th power, and then b to the 1st. But in this case, b is minus b to the 1. Okay, so once you have that negative sign, you're going to take it with you in your second term, that negative b. Plus 5 choosing 2, 2a to the 3rd, negative b squared, plus 5 choosing 3, 2a to the second, negative b to the third, 5 choosing 4, 2a to the first, negative b to the fourth, plus 5 choosing 5, 2a to the 0, and then we have negative b to the fifth power. Okay, so once again, let's simplify all of those. 5 choosing 0 is 1. So we have 1 times 2a to the fifth, which is 32a to the fifth, plus 5 choosing 1 is 5. 2a to the fourth is 16a to the fourth. And then it's times negative b, and it stays negative because it's only to the first power, plus 10, 8a to the third, and then negative b is actually going to become just b squared, because when you take a negative value to an even exponent, it becomes positive. So then we have 5 choosing 3, which is 10 again, and 2a squared is 4a squared. Negative b to the third stays negative b to the third, plus 5 times 2a times positive b to the fourth, and then we end with 1 times negative b to the fifth. And this last row we're going to write is our final answer. So the first term stays 32a to the fifth, plus 5 times 16 gives me 80. However, we also have negative 1. So this plus sign I'm going to get rid of, and it's actually going to become minus. So minus 80a to the fourth b. We have 10, 8, and then 1 here, so it's plus 80, again coincidentally the same. A to the third b squared. 10, 4, negative 1, minus 40, a squared b to the third. 5 and 2, plus 10, a b to the fourth, and then your last answer is negative b to the fifth, so it's minus b to the fifth. So notice how we are alternating our signs when we have a value or a term in our original binomial that's positive or negative. Or I'm sorry, when it is negative, the signs alternate. So again, this is your final answer. So if you are given a binomial like number 4 that is asking you to take it to the 10th exponent, that would take you forever. So what I'm just going to do to educate you on this, but also to keep it manageable, is only ask you to give like the first 3 or 4 terms. So we're going to do the first 3 terms. So we have 10 choosing 0 times a, which is 2x, to the 10th, sorry. And then we have 10 choosing 1, 2x to the 9th. And then our b value is actually y squared here. Y squared to the first, plus 10 choosing 2, 2x to the 8th, and then y squared to the second. So when we simplify, we get 10 choosing 0 is 1,024. I'm sorry, 10 choosing 0 is 1. 2 to the 10 is 1,024. X to the 10. Plus 10 choosing 1, which is 10. Times 2 to the 9th, which is 512. X to the 9th, times y squared, because it's just y squared to the 1. Then we have plus 45, which is 10 choosing 2, times 2 to the 8th is 256, x to the 8th. And then y squared squared, you're going to multiply those two, and you're going to get y to the 4th. So when we simplify, our first term stays the same, 1024 x to the 10 plus 10 times 512 is 5,120 x to the 9th y squared plus 45 times 256 gives us 11,520 x to the 8th y to the 4th. Yes, the numbers are huge because we are raising it to the 10th power, so that should make sense. Now, earlier I said a couple of things to remember, and the first thing was, well, the number of terms, the number of terms you have after you expand is one more than the exponent we started with. Well, our exponent is 10, but I only asked you for the first 3, so you're not going to have 11 terms. And then the other thing I said was take all of the exponents and they should always add up to give you 10. Well, the first one does, but this gives you 11 and this gives you 12. Well, that is because you have y to the 2nd as your b value. So if one of your coefficients has its own exponent other than 1 to begin with, then that rule won't apply. So that's the one exception. But if we went back a slide and we pointed this out again, and I said, okay, well, that adds to give me 5. 4 and 1 gives me 5. 3 and 2 gives me 5. 2 and 3 gives me 5. 4 and 1 gives me 5. And 5 gives me 5. And then it's to the 5th power, so we should have 6 terms. 1, 2, 3, 4, 5, 6. So it's nice little things to remember as you go along and complete these problems. All right, the last thing, the last part of this is if I wanted just a specific term. So for example 5, it says find the 4th term in the expansion of x plus y to the 15th. Well, I'm not going to do all the way to the 15th just to find the 4th term. What if I ask you for the 10th term? That's crazy. So let's just find the term I'm asking for. So the first thing you need to identify is n and r. So n is going to be the same n that it's always been, which is this exponent right here. But then r now, if you look over to the right, there's a little box that says r is k minus 1. Well, what is k? K asks for the kth term. So if I'm asking for the 4th term, k is 4. So let's put this in a problem. So the first thing I'm going to identify is say, okay, well, k is 4 because I'm asking for the 4th term. Therefore, r is going to be 4 minus 1, which is 3. And we know that n is 15 because that matches the exponent on the binomial that I'm beginning with. So n choosing r, which is 15 choosing 3, is the coefficient of the 4th term. And then you have x, your first term, to the power of n, which is 15, minus r, which is 3. And then our b value, which is y here, our second term in the original binomial, is just to the r power, which in this case it is 3. So if I expanded all of this, 15 choosing 3 is 455. X to the 15 minus 3, which is 12, y to the 3rd. And that is the 4th term of that binomial. So now if we did it with some coefficients, well, k is 9 because I'm asking for the 9th term. Therefore, r is 1 minus 9, which is, 9 minus 1, 1 less than 9, which is 8. And n is 12 because that's the original exponent I started with. So that gives us n choosing r, which is 12 choosing 8. Then it's 3x, because that's my a term, the first one, to the 12 minus 8 times negative 2y, my b value, to the r, which is 8. So 12 choosing 8 is 495 times, so this becomes 4, so we have 81 x to the 4th, and then we have positive, because it's an even exponent, 256 y to the 8th. So when we multiply 495, 81, 256, yes, it's huge, 10,264,320. And then you have your variables x to the 4th, y to the 8th. So that's how you find a term in the middle of a huge expansion.